I try to keep things simple, so don't hold me to being exactly accurate. Our motto is close enough for lay humans, okay? I've been told that the term layman is not politically correct, so lay humans it is. As for questions or comments that come up, oh, hello, welcome. So I don't believe in holding them to the end, because when you think of something, you have a question about something, bring it up now when it's most relevant. When it's on your mind, maybe there's a question you have that's holding you up from understanding something, and we don't want to move on because then you'll get more confused, or you have something thinking out. I think it's better, instead of holding it to the end, just to bring it up. But do raise your hand, okay? Don't just blurt it out. The reason I added in this rule is because one time, giving a lecture, I'm telling a joke, and I'm just about to give the punchline of the joke, and somebody chimes in, oh, I have a question about, God, I couldn't believe someone did that, and I have to tell people, raise your hand, okay? See, middle of a joke. Okay, also, what do you have to say, whether it's a question or a comment, keep it brief, short, okay? I know a lot of people like to think, oh, this is my turn, this is my 15 minutes of fame. No, not here, okay? People came to hear me lecture, not you. You want to talk, get your own lecture, okay? Like people, maybe they'll come, okay? And the other thing is, please don't be offended if I decide not to answer your question or address your comment. I have to judge. I want to keep everyone engaged, okay? If you want to get into some particular discussion, you can talk to me later. But I want to address questions and comments that are relevant to what I'm teaching, that are going to be at a level that everyone's going to follow. I don't want to get into a one-on-one during the lecture. I want the question and comments to be something that everybody can enjoy, and I will judge that. Again, I have to put in this comment because one time, somebody raises a question, and I say, well, I don't think that's appropriate, let me move on. And someone's yelling out, shaming me, why did you just answer his question already? I can't believe it, give us some credit, okay? If I don't answer a question, I have a reason, a good reason for it. And again, you can talk to me afterwards at a break, one-on-one. Here's my email, you can write to me or contact me on Facebook. Okay, so, end of the lecture. The first question, you might wonder, since you're attending a lecture on quantum physics, why should I care about quantum physics? Well, okay, for me the answer is easy. I make a living. But why should you care about quantum physics? Well, there are two reasons. The first reason is that it's all around you. It's part of our lives, okay? Unless you're living in a cave, and maybe even then, it's just everywhere. You might not realize it, but just everything you see here would not exist if it were not for quantum physics. We wouldn't have cell phones, computers, communications, DVDs, digital cameras, games, solar cells, maglev, lasers, MRI, LEDs, and all kinds of things. These would not exist without quantum physics. The only way that it was possible to invent these things is because of quantum physics. No one could possibly have ever invented these things without it. So it's very important from a practical standpoint. By the way, since I mentioned LEDs, I have to brag and say that one of my mentors at UCLA invented the LED. Whoa! So he's gone now. He passed away a few years ago. So I dedicate this lecture to his memory. So you might wonder, well, how did quantum physics make all this possible? Well, let's take one example. In 1945, the biggest computer in the world was built for the Army, and it was made out of non-quantum devices. It was made out of vacuum tubes. You might remember vacuum tubes from the old days that, you'd have to go to the drugstore when one burnt out. And sometimes very powerful amplifiers and things still use these. But this computer had 20,000 of these things. And these things, not only are they big, but they generate a lot of heat, they take a lot of space, there's a lot of... It took an entire city block to build this giant computer, the biggest computer in the world in 1945. Well, then quantum physics existed, but it took, it was a couple of years later when at the AT&T Bell Labs, they used quantum physics to invent the transistor, which replaces the vacuum tube with something that occurs at an atomic level. On the lower right here, we have a photograph, not a normal photograph, it's an electron photograph, of a very tiny transistor. To give you an idea how tiny that is, you see kind of a checkerboard pattern of, black and white spaces. Each one of those white squares there, that's one atom, okay? That's how small we can make transistors, and it's probably smaller now since this photo was taken. So it gives you an idea. Okay, and think of a cell phone. A typical cell phone has got about 2 billion transistors. Probably now it's probably much more than that. So your cell phone has got 100,000 times the computing power of the biggest computer in the world that took up an entire city block. Just imagine the impact that has on technology. So that's a practical application. But quantum physics is also very important, and this is the focus of this talk today. It has a philosophical importance because quantum physics has revolutionized the way that we think. It's shown us that the universe is just nothing like what people used to think. And that's the idea that I want to get across to you. And this has impact on our philosophy, how we view the world, how we view ourselves, how we think about what's going on and what does it all mean. Quantum physics comes into that. Now, you might think I'm exaggerating. Oh, he's a physicist. He likes to make his stuff sound really important. Well, you don't have to take my word for it. I'll give you some other quotes of some great physicists. You might have heard of this guy. He says, if quantum physics is correct, it signifies the end of physics as a science, okay? Is that revolutionary or what? Okay, Werner Heisenberg, you may have heard of. Not only is the universe stranger than we think, it is stranger than we can think. The universe is so strange, our minds are not capable of seeing how strange it is. Niels Bohr will talk about a lot. Everything we call real is made of things that cannot possibly be regarded as real. You may not have heard of this guy, Daniel Greenberger, but if I quote someone here, it's not some guy who has a blog. It's a great physicist, great renowned. Quantum physics is magic. You ever think you'd hear a physicist say that? And Sir Roger Penrose. Quantum physics makes absolutely no sense. Okay, so I'll be trying to convince you of all these things. And, you'd think they'd be talking about some weird kind of speculative stuff, things that aren't really proven, pyramid power, anti-gravity, time machines, human auras, and all this crazy stuff you hear about. You'd think they'd be talking about that, right? But they're not. They're not talking about that. Okay, now all these speculative things, okay, I'm not saying that they're not true. They might be true, and in fact, all the science that is now proven and accepted as true, at some time in the past, it was speculative, okay? Someone came up with an idea, and it took a while till they could prove it. But I'm not talking about that in this talk. In this talk, I'm not discussing theories that have not been proven, except when I get to philosophy. Philosophy, of course, can't really be proven. But all of the science, all the physics that I'm going to talk about is proven stuff, okay? But the mysteries that I'm going to present, these philosophical mysteries, it opens the door to show that any speculative ideas about science, they could be real. Basically, one thing that quantum physics has taught us is that nothing is too absurd, too ridiculous to be true. Because quantum physics, I'm going to show you, is totally ridiculous. It's fantastic. It's absurd. It's just stupid. And yet, you ask any respectable physicists in the world, they will tell you it is absolutely true. No one doubts. If anyone says, oh, I don't know if quantum physics is true, they're not a physicist. They're a fact. Okay? Believe me, it's been proven over and over and over millions of times. It's true. It's absolutely true. So I'm only talking about proven science. So every Nobel laureate, every respectable physicist, every accredited university, every textbook agrees quantum physics is true, period. Okay? The theories have been examined for the decades. You know, they keep refining them and improving them, you know, fixing them and extending them. But no one has ever been able to disprove it. And all the experiments, it's all based on experiments. You have to do experiments to prove things are true. These experiments have been repeated over and over for decades. The results always agree, okay? Or if they're slightly off, they fix the theory a little, they make it agree. So there's no doubt in any of this. And again, the proof is in the pudding. You know, these devices that make, they work, okay? If you put a pyramid on your head and you claim it gives you energy or something, there's going to be questions. Does that really work? You know, well, but if someone asks you, does your cell phone work? Well, okay, maybe your cell phone doesn't work, but most people's cell phone, it works. Okay, there's proof right there. And again, I'm only going to be discussing, as far as the science goes, proven science, okay? So you might attend physics lectures, they're going to talk about wild, crazy, far-fetched, crazy-sounding ideas about speculative science that some handful of weirdos believes in. But I'm going to tell you about far-fetched, crazy, wild, crazy-sounding ideas about proven science that are completely accepted by all respectable scientists. So there is no doubt that quantum physics is true, and yet there's a huge controversy, okay? It's more than a century later, there is still raging controversies over it. So, did I just contradict myself? How can there be controversy if everyone agrees? Well, they agree on the physics, the science, the physics, the math involved. They all agree, that's true, no doubt. But when you start to look at it philosophically, metaphysically, mythologically, what does this mean? What is this telling us about the world? You know, now you're getting outside the realm of physics. There, the controversy has been raging for, 120 years, and it hasn't ended. And there's no sign it's ever going to end. So there are a lot of views. And I'll be presenting a variety of philosophical, metaphysical views about quantum physics. And the views I'll present are not the weirdos. They're ones taken by globally respected physicists. A lot of them appear very questionable to me, and I don't buy them at all. But I'll try to be objective and try to make it clear when I'm giving you my own opinion, which is not universally accepted. Okay, so the idea that philosophy is affected by science might sound kind of strange to you, but actually this is a very old idea that goes way, way back, long before quantum physics, and I'll give you some examples of that. We'll start with the old theory that the Earth is the center of the universe. Everything, all the planets, all the stars, and the sun itself, they all revolve around the Earth. And you can see, this is not just a scientific statement. I mean, it's wrong, of course. It's not just scientifically wrong, but it has a philosophical idea. Our planet, where we live, is the most important place. Everything revolves around us. We are at the center of the universe. Nothing in the universe is more important than where we live. Okay? Well, now of course we know that's not true at all. We're just one of a bunch of planets going around one star, and there are billions of stars, and we're not a big deal. We're not special. Our Earth is, maybe it's special because we're on it, but we think so. But the universe does not revolve around us.
There's a philosophical implication there, and that includes you. It doesn't revolve around you or you or you.
Another idea. Okay, I know some of you are saying, oops, he made a mistake. First time in history, Bradley Boggs has made a mistake. He put up the same picture as last time. Well, no, that's not a mistake. That's just efficiency. I realized I can use the same picture for two different ideas. Okay? So now the point is not that we're at the center. The point is, look how small the universe is. You know, there's the Earth and the planets and the stars, and it's like it's all very compact. You know, it's just this little universe. It's not much bigger than the Earth. It's just around us. Well, again, it's an idea about, you know, our importance in the universe. You know, we're even if we're not at the center, we're still very important because we're a big part of it. Well, now we know that the universe is much, much bigger than they used to think. It just goes on, and what we can see is only the beginning. There's so much more beyond it that we can't see, and we have no idea how far it goes, how big it is. And, you know, we look with telescopes out into the sky, we can see all of these things, and our entire world, not just the Earth, not just the solar system, our entire galaxy is nothing but a tiny speck in this picture. So again, it puts the importance of our lives in a different philosophical perspective. Again, saying, we're not that important, you know? Or if we are, it's certainly not backed up by our relative size in the universe. Also, we can look at the same thing, not just in terms of space, but in terms of time. You know, people used to believe that basically the history of the universe is the history of us, the history of humans, you know, except for there was 6 days at the beginning. Oh, that was nothing. After that, it's all about us. All of history is about the history of mankind. Well, now, anyway, a lot of people have come to realize that it's not this way at all, that the universe is 14 billion years old, and a lot of stuff happened before we came on the scene. And the entirety of human history is just a speck in the entirety of time as we know it. Again, putting in perspective, how important are we? What went on in the universe for all of that time before we came on the scene? And all that time after we're gone, maybe. Another idea, an old idea, is about light. Okay, this is very relevant. I'll be talking a lot about light. And long ago, people used to believe that humans create light. Light comes out of our eyes, and it enables us to see. The way we see something is we send out a light beam, it hits something, and we see it that way. And that might sound pretty stupid to you now, but they were thinking of it in terms of like touching. Okay, if I want to touch something, it doesn't come to me, I have to reach out to it. Oh, there it is. I touched it, I sensed it by reaching out to it. And they thought it was the same thing with light. Well, now we've, again, thinking, oh, we're so important, we create light, and, you know, light exists only for us. Well, now we found it's very different. Light comes from other places, most of the sun. Almost all light comes from the sun. And it hits things, and the light goes out in all directions, and just that some tiny fraction of it just happens to hit your eye. Okay, light's going out all everywhere, but the only reason you see things is because your eye happens to be in the way of some tiny, tiny fraction of that light. And again, light exists independent of us. It doesn't exist for us. Another old idea is that if things are solid, they're, you know, that's what they are. They're solid. They're just packed full, you know, it's not like a gas. Well, we found since that things are not solid at all, even when we call them solids. If you look at like a crystal, this might be like a salt crystal. If you were to look at a small enough scale, you see inside that crystal that it's made up of a bunch of atoms, which are pretty far apart from each other relative to their size. It's almost all empty space in between. And then not only is there lots and lots of empty space in between the atoms, but then you look inside one of the atoms. The atom is almost completely empty space. There is basically almost nothing in the atom except you've got a little nucleus and little electrons and lots of space. So when you see something that's looks solid, actually it's almost completely empty. Okay, so everything we see is actually mostly emptiness, including us. See how I turned that, made that philosophical? You know, everything's solids are empty. We're made of solids, so it means we're empty. And of course, some people are much more empty than others. Another old idea is that it was thought that in order to affect something, you had to contact it, okay? You might contact it directly by touching it, hitting it with a stick, or more indirectly, you might blow on it. Again, you're using air to push it. You have to make some kind of physical contact unless you can go outside of science. If you're a witch or a sorcerer, then you can go into the supernatural. You don't have to rely on science and natural forces. You could go beyond that. But we've since realized that you don't have to be a witch. Anybody can affect things without touching them. For example, magnets, right? Just take a magnet. You can move things without making contact with them. Another example is gravity. Okay, we don't have much gravity, but like our Earth pulls the moon around it by gravity, okay? The Earth is not touching the moon, certainly, but it pulls it around. This is called action at a distance. And long ago it was thought, oh, action at a distance is that's supernatural, it's beyond science. Well, it's very much within science. But I wanted to introduce this idea in particular because next week, in part 2, I'll be talking a lot about action at a distance. So again, you don't have to touch to have impact. Kind of, again, maybe getting philosophical. You don't have to touch something to have an impact on something. Nature is used to doing that all the time. You don't have to go to supernatural, have special supernatural powers. And then the last example I'll give, you don't have to go too back and far in time. This is actually contemporary with quantum physics, rose just pretty much the same time. And people used to think that the universe was absolute. Physical quantities are the same for everyone. We're observers and we just see the way that things are. And it turns out, you may have heard of the theory of relativity, that a lot of things are relative. There's no absolute to them. I'll be mentioning a little bit more about this in the second half, in part 2, about relativity. This talk is not about relativity, but there are some places where it enters in. We'll touch on that, but again, getting back to the idea that, well, maybe we are important because, things are just the way they are without us. It's like when we observe them, that determines how things are. Relativity is part of that, as well as quantum physics, as we'll see. Things are relative. They're relative to us. Again, there are kind of philosophical implications. It's like, what is real? Maybe that depends on us. We have importance in that, So kind of turning, swinging back, pendulum swinging back the other way. And we're not going to take the time for this, but sometimes I give this course at more of like a discussion group where we, don't have a time limit, but I'll just show, we'll raise some discussion questions and we can get a discussion going. But I'll just let you see it and think about it for now. Okay, so let's get to quantum physics. And the first question is, what does quantum mean? What is a quantum? Okay, a quantum is a unit of quantity. Okay, think if you have a quantity of something, it's made of, so if you have time, that's made up of seconds. If you have distance, that's made up of inches. If you have quantity, the quantity is made up of a quantum. A quantum is a unit of quantity. It's the smallest unit of quantity. Okay, so what one quantum is, it's the smallest possible amount that you can have of something. The only way to have less of it is to have nothing, to have none of it, okay? So, some examples of a quantum. These are not usually what quantum physics deals with, but some simpler examples. Before we get into the trickier examples, electricity. What's the smallest amount of electricity you can have of electrons flowing? The small amount is 1 electron. Okay, you can't have less than 1 electron flowing. There's no such thing as half an electron. Okay. Also, like, say, an element, say carbon. The smallest amount of carbon you could have, 1 atom of carbon. So an atom is 1 quantum of one of the elements, okay? Now you might say, well, wait, I can have less than 1 atom. I can split the atom. I've heard about people splitting the atom, you know? And yes, it's true, you can certainly split the atom. But the thing is, when you split it, if you were to split a carbon atom, say, then it's not carbon anymore. So 1 atom of carbon is the smallest amount of carbon you can have. 1 atom of uranium is the smallest amount of uranium you can have, etc. Okay? Also, say smallest quantity of, say, water or compound would be 1 molecule, H2O. Okay? So you can't have less than 1 molecule of water. Again, you can split a molecule. You can take H2O and you can split it into H and OH. That's pretty easy to do. But then it's not water anymore. So you cannot have less water than 1 molecule of H2O. So anything that's quantized means you can have none of it, or you can have 1 quantum, 2 quantum, just plural of quantum, 3 quantum, etc. You have to have a whole number of quantum for anything that is quantized. So, I don't know if anyone else has done this, but it made me think about how far can we push this idea? What about a quantum of human population? What is the quantum? Think about population is quantized because it can only be a whole number. You can have 0 people, no people, or you can have 10 people, but you can't have like 2.5 men. I mean, that doesn't make any sense, you know? It has to be a whole number. But now this raises some interesting philosophical questions, okay? Again, getting into philosophy. What's the minimum quantity of a human? What's the quantum of a human? Well, is that the quantum of a human? This gets you into some very interesting philosophical, controversial political discussions. What if you have a person and you take part of them? Is that still a human? You know, how much of a person do you have to take and still count that as 1 human? Or maybe not even a person, maybe just a brain, maybe just part of a brain. If you take a brain, if you think, well, a brain is 1 person, now you start to cut up parts of the brain. At what point is it no longer a person? Or maybe the part is another person. It gets you into some interesting philosophical questions, anyway. Well, after this ridiculous tangent, I thought of an even more ridiculous one. What is the quantum of AI? Okay? AI has certainly been of great interest, but I was thinking of an example of AI that goes back many years ago. I'm sure a lot of you are familiar with this movie, what was it called? 2001, A Space Odyssey. Came back long before people were thinking about AI, but this movie had an AI in it. And there was a very interesting scene in that movie. If you remember the movie, it's about a spacecraft and a bunch of astronauts on this spacecraft, and the spacecraft is run by this AI. It's a computer it's more than a computer, it thinks. And at some point, the astronaut decides, I don't think I want an AI running my spacecraft. And if you saw the movie, you'll understand why he felt this way. So he wanted to take this AI and reduce it from 1 AI to 0 AI. He wanted to go below the threshold of 1 quantum of AI and reduce it to just, instead of being a real something that thinks, just a stupid computer that does what it's told. You couldn't just unplug the thing and turn it off because This is running all the life support systems, navigation systems. You're not going to have a spacecraft without computer, but he didn't want an AI computer on it. So it's very interesting, this scene in which he starts physically pulling boards out of this AI one at a time while the AI is talking to him, while this is happening. And you see at each step, the AI is getting stupider and stupider and stupider until he pulls out a board and the AI stops talking to him, and he realizes, okay, now I have what I want. I just have a stupid computer that'll do what it's supposed to do and not get its own ideas about how things should be run around here. Okay, let's get back to quantum physics and some history. How did it start? Okay, just before it started, just to give you an idea of how the world, or how the world of physics, how physicists viewed the state of physics. Albert Michelson, great physicist, Nobel Prize. His view was that 1899, physics has discovered everything, basically. We basically know everything there is to know. Physics has come so far that all that's left to do is just little details. Like, he says, things like finding the sixth place in decimals. What does he mean by the sixth place? Well, let's say that the speed of light in vacuum, let's say they knew it was this, and somebody makes a great discovery. Oh, it's not that. There's actually a 5 there. Okay, whoopee. Okay, exciting. This is what he thought. That was all that there was left to do in physics. Boy, was he wrong. Okay, as you're going to learn, quantum physics came soon after this and just turned physics on its head. Okay, he had no idea what was coming. Okay, so how did quantum physics start? Quantum physics is usually called quantum theory. I like the name quantum physics. It's also called quantum mechanics. I don't like that name so much because I tell people I do quantum mechanics and they think I know how to fix their car or something. And originally it wasn't about any of the examples of quanta, plural quantum, any of those examples. How it started is physicists were trying to explain the colors that radiate from something they call a hot black body. Well, what is a hot black body? It's not what you might think. It's something in physics which, when it's cool, it's black. Okay, like the picture here on the right shows a cast iron coming out of a furnace. Well, when the cast iron is cold, it's black. But when it's hot, it's glowing. It's glowing. This cast iron is not orange in the sense that a fruit of orange is. That's just orange. That's its color. This is a color that it glows from the heat. It's a color that's actually coming from the heat much more than it is coming from the object. Okay, and this is a common phenomenon, and we see it all the time. Things are glowing, red hot, white hot, whatever, orange hot. And they figure, well, gee, physics has come so far. Of course, we can explain this, right? We're physicists. We know everything. So they tried to explain it, and they failed. They failed miserably, or as Jimmy Durana might have said, it's a catastrophe. So all of the theories, all the greatest scientists in the world were trying to explain such a simple experiment, and the theories were just dead wrong. I'm not talking about inaccurate. I mean just like completely wrong. And this was not only frustrating to them, it was very humbling because, as I showed with the example of Michelson, physicists thought, oh, we know everything, and now they found we can't even explain this common phenomenon. So they were predicting huge amounts of ultraviolet radiation. The experiments showed there was almost none. So to make it dramatic, they called their failure the ultraviolet catastrophe. Okay, people other than physicists might not have thought it was a catastrophe, but physicists thought it was a catastrophe. They couldn't explain it. Well, welcome to the scene, Max Planck. Okay, and he had an idea to try out, and the way he stated is there is a least thing that can happen. So he was kind of introducing almost the idea of the quantum. It's not like there's no limit to how small a thing that can happen. It's like there can be nothing happening, or there can be one quantum happening, and you can't have something in between. You know, it's just like you can't have any less electricity than one electron. You can't have anything less happening than one quantum of happening, of something happening. So the only way you can have less than this one quantum of happening, you didn't call it quantum yet, that came later, is that there's nothing happening. And, I like this picture of Max because it shows him in front of a blackboard with equations and diagrams. And if you look closely, you can almost see a halo around the head of Saint Max, who came to save physics from the ultraviolet catastrophe. Well, his idea would later be called a quantum leap. You may have heard of a quantum leap. And basically he's saying that energy is quantized. Energy cannot just change by any amount you want. It's either changes by at least one quantum or more, or it doesn't change. There's a minimum amount. So I show here kind of a diagram where the vertical scale is like how much energy something has. And we have the energy going from level 1 to level 2. It can't go continuously down. It has to leap across. It's at level 1, and then now it's at level 2. It leaped across, and it was never anywhere in between. So it's made this leap. It's changing in discrete, tiny steps, quantum leaps or quantum steps. And if that doesn't sound strange to you, let's just suppose that the speed of your car was quantized, and one quantum of speed, let's just say it's 10 miles per hour. So let's say your car, it could be stationary, but then as soon as you try to accelerate, suddenly it goes from 0 to 10 miles per hour without ever being at any speed in between 0 and 10. And it could be 20 or 30, or any multiple, but it's impossible to go 1 mile per hour or 6.7 miles per hour, anything like that. It can only go, and then it's just, what a strange car that would be, okay? Now that's not accurate, but you get the idea that this is bizarre. So, so the reason it's called a leap is because you can't stop partway through. Okay, you can't have half a leap or any fraction of a leap. It's all or nothing. That's why it's called a leap. Not because it's big. People think of a leap, oh, I'm taking, big leap. No, it's not that kind of leap. It's this kind of leap where this guy, either he's going to leap across the chasm or he's not. If he can't make it across, he's not going. Okay, it's all or nothing. But in the case of a quantum leap, it's generally a very, very tiny, tiny leap. It's a leap which is so small that it's impossible to have a leap that's smaller. The only way you can have a smaller leap is to have no leap. Okay? So that's the idea. Well, I'm sure you've heard a lot of people talk about quantum leaps and, wow, I'm taking a quantum leap. It's such a big, big leap. And this bugged me. If any of you who know how I am, you can imagine how much this bugged me. And it turns out that one of the scientific magazines that I subscribe to, they actually had a monthly column. They'd have a special section called Technically Speaking, and they would have, articles about what bugs them about the way that people use scientific language. Well, so I wrote an editorial for this, and they published it. It was so long it took up like the entire section that month. And in it, I described how terrible it was, what a catastrophe it was that people would talk about a quantum leap as if it was something big. And as an example, and the thing that actually provoked me to write this article, I had seen a television ad by some technology company. They were making some high-tech equipment. And in this commercial, they say, we're taking a quantum leap into the future, and it's supposed to give people these grandiose ideas. Oh, they're taking quantum leaps. Wow, aren't they advancing? And I thought about, what exactly are they saying? They're taking a quantum leap into the future. What they're saying is that the rate, the step that they're taking in advancing technology is so very, very, very tiny that the only way they can make less of a leap is if they did nothing at all. You know? So now that you know what a quantum leap is, you know, you can think about if you've taken a quantum leap, and why do you call it that? Why is it truly a quantum leap? And the hint is that just because it's big doesn't mean it's a quantum leap, okay? It's an all or nothing thing. Well, okay, Planck solved the catastrophe, as I mentioned. But the problem is, nobody understood why this worked. He just came, let's take this idea and run it up the flagpole and see what happens, see if anybody salutes. And it solved this mystery that none of the world's greatest physicists could not solve. But then everyone started thinking about it. Thinking, what? Quantized leaps? What's going on here? What does this mean? And nobody understood, and that includes Planck himself. He said, what I did was an act of desperation. It's like, I didn't have any reason to think that energy is quantized. I just said, well, let's take this idea and see where it goes. And it worked. So it was a big mystery to everyone. And so you might say, well, quantum physics was not really started yet. Well, by the way, this catastrophe, not all physicists would acknowledge that it was actually a catastrophe. You know, even though all of the known theories completely failed, there was one physicist, James Jeans, who said, oh, it's fine, theories don't need to match all the experimental results. You know, even though the experimental results were like totally wrong. He thought, big deal, close enough for physics, you know. What a great scientist. Max Planck had an opinion about that. James Jeans is an idiot. Well, James Jeans, after this, he did come up with some important theories. He actually came up with one of the models that kind of works, sometimes works, for the black body radiation. But he went on to develop the famous steady-state universe theory, okay? Have you all heard of the steady-state universe theory? No, none of you have heard it, because that was totally trashed and thrown in the physics garbage pan forever after, you know, Hubble's law and the Big Bang theory showed that the steady-state universe theory is total garbage. Okay, so, let's see. Why did Boltzmann come up at this point? I forget, but anyway. So, you've probably all heard the joke, who's buried in Grant's tomb? Okay, it's just kind of like a stupid riddle, you know, who's buried in Grant's. Well, let's take a twist on that. Whose equation is on Boltzmann's tomb? Boltzmann was a great chemist from the 19th century, and here's a picture, here's a photo of his tomb, and you'll see above the bust there is the famous Boltzmann equation, okay, with the letter K in there. That stands for Boltzmann's constant. Well, is that really Boltzmann's equation or Boltzmann constant? No. Actually, that's Max Planck's equation and Max Planck's constant, okay? And somehow, you know, they gave Boltzmann credit for it. And I guess Max Planck didn't want to be a party pooper and say, hey, that's fine. So that's the way things go in physics. You know, people try to be humble. But eventually Max Planck did get his reward. Many years later, there was another constant that Planck had also come up with, and that was named Planck's constant. So he did finally get it. He was too humble to name it himself, but the great Niels Bohr, one of the greatest physicists of all time, talk about a lot, named it Planck's constant. Well, the impact of quantum physics. was from the start. It was quite revolutionary, as I mentioned. Just to give an example, what was the impact on Max Planck himself? Here he is a little time before he more or less invented quantum physics, and here's a photo of him after he invented quantum physics, and you can see it has a big impact. Well, so he had got the ball rolling, but he didn't quite have it. The person who is often credited with the invention of quantum physics is maybe Max Planck, or maybe it's a different guy. A different guy who was a nobody. He was 26 years old, and he had a PhD in physics, but he could not get a respectable job for a physicist. He could not get any kind of research position, professor position. The only job he could get was to be an examiner in a patent office, okay? Not a real prestigious position for the physicist, but he was earning a living. But while he was doing that, he was doing his own research on his own time. He had access to, of course, the patent office had vast science libraries. They got copies of all the journals, and so he could keep up on what was going on in the world of physics and read all about it. And so, working this way in his spare time, he published a number of papers. In fact, in 1 year, he published 4 papers. All 4 of these papers turned out to be 4 of the most important papers ever published in the entire history of physics. Okay, amazing, in 1 year. Theory of Brownian motion, I'll explain next. Theory of the photoelectric effect, we'll get to. The theory of special relativity, I'm sure you've heard of. And I'm sure you've heard of the theory of mass energy conversion equals mc squared. Everyone's heard of that. One of these 4 would eventually earn him the Nobel Prize. Don't speak out, but you might think in your own mind, you might make a guess. I'll give you the answer later. Which of these 4 would get him the Nobel Prize? But let's talk first about Brownian motion. This is the random motion in pure water. So for this experiment, they wouldn't take pond water that's got all kinds of junk in it, things living in it. They would take distilled, perfectly pure water, and they would put it in a place where there were no vibrations. There was nothing that could jostle it at all. And look at it under a microscope. And they'd take a tiny speck of dust or a tiny pollen grain, and they'd float it on top of this drop of water and look at it in a microscope. And then what they would see is that the speck would be wandering around. And they'd be wondering, what is making it move? There's nothing alive in here. There's nothing, in there. There's no vibrations. Why is it moving? And it moves in a very strange way. And some biologists said, oh, look, spontaneous generation of life. We took pure water and life just appeared in it. Well, that was ridiculous, of course, but here we show a picture of what's going on. So when you look under a microscope, all you see is the yellow circle. That's the pollen grain. The other thing is the gray spots under there, totally invisible in a normal microscope. But Einstein supposed that this water is made out of molecules, and these molecules are jumping around randomly. And he did a lot of math, and he calculated, if this were happening, how would that yellow speck move? What are these statistics describing how it moves? He did that, and it turned out it matched exactly the experimental results. And this was a very important discovery because this proved that molecules exist. Molecules and atoms exist. You may not realize, but even back in the year 1900, it was not known. I mean, a lot of most scientists believed in atoms and molecules, but there was no proof that they existed. So they could not be accepted as known physics because there was no proof of it, and good physicists don't accept anything until it's proven. Einstein was the first person to prove that atoms and molecules actually exist, and after that there was no doubt. So finally, all scientists were convinced. It's hard to believe that in the year 1900, there were still college textbooks in respectable colleges, chemistry textbooks that would have no mention of atoms and molecules in them because the professor didn't believe in them. But all that ended in 1905 with Einstein's first publication in that paper. And again, this ties in with quantum because, as I mentioned, an atom and molecule are quantum. But the second paper that he published was about the photoelectric effect. Okay, that may sound like a strange name, but photo means light, electric is electricity. So all it is about converting light into electricity. Okay, so like a digital camera or a solar cell, you have light, you put in light, and you get electricity out. Okay, that's the basic idea for digital cameras and solar cells. But back in 1900, the way they did the experiment, they didn't have digital cameras or solar cells, of course, but they could have a vacuum chamber here with electrodes, and they would shine light on one of the electrodes, and it would make electrons come off and flow across, and then they could measure how much current, how much voltage there is. They could change how strong the light is. They could change the color of the light. So, simple experiment, and wouldn't you know, no one could explain it. Again, with the catastrophes. Again, physicists who thought that they could explain everything, fairly simple experiment, and their theories were garbage. Their theories, total failures. It's just, all the world's greatest physicists, no one could come anywhere close to explaining what are the equations that control this. Well, Einstein looked at the data. He didn't have a lab. He didn't work at a university. All he had was a library and his own brain, and could make his own calculations by hand. They didn't have computers, of course, or calculators. And he figured all this out on his own. He came up with a theory for this. And, he had access to the experimental data from the journals. And here's how his theory worked. He started with Max Planck's idea. He was inspired by this idea of the quantum leap and all. Energy is quantized. And he imagined that light energy is quantized, so light is made of quanta. So you can have one quantum of light, and that's the minimum amount of light you can have. Okay, this quantum was later called the photon. So you can have no light, you can have no photons, you can have one photon, two photons, three photons, but it has to be a whole number. Okay? And then he said, well, the idea of how this experiment works is that you have one quantum of light, one photon, hits the metal surface, and it knocks out one quantum of electricity, one electron. Sounds like a simple idea, and yet no one had ever come up with this. No one had had any reason to come up with an idea of this. And just using this simple idea, he was able to explain all the experimental results that no one else could come close to. And to answer the quiz question, this is what he got the Nobel Prize for. It took 16 years for the rest of the world of physics to be convinced of this, because this was not an easy idea to accept. But eventually he did get the Nobel Prize for that, and not for the other things you might think he got it. Well, you might wonder, well, where did the name photon come? That came a little later. Well, one theory about where they got the name photon is, well, photo, means light. Probably heard, photograph, photo this, light. And the suffix on, that's like a particle, like an electron, proton, neutron, they're all end with on. So you put those together, you get a particle of light. Okay, sounds reasonable. But there's an alternate theory. Okay? And that theory, which I'll thank to in the audience here, was Susan Crystal Moon Lumiere, came up with an alternate theory. Well, pho, we all know, is a Vietnamese meal, and it's a light meal, right? Light is a light meal, and it's a light meal. It's an alternative to wonton. So you can have a wonton if you want a heavy meal, or a photon if you want a light meal. So maybe that's where it got its name. Okay, so Einstein came up with this theory inspired by Planck. You'd think, well, Planck must have been overjoyed. Wow, his crazy idea had actually led to something really important. That's what you would think, right? Right? Wrong. For some crazy reason, I can't understand, Planck thought that Einstein was all wrong, okay? I mean, here he'd come up with this idea of the quantum leap and all this, and Einstein said, hey, take this idea and it explains all the equations. Einstein said, no, that's ridiculous. Go figure, you know. Einstein wanted to publish his work in the premier journal, the Annals of Physics, but Planck was the advisor for the journal on theoretical physics. And they would not publish Einstein's article, the article that later won the Nobel Prize. They would not publish it unless Max Planck approved. Well, Max Planck approved it, even though he completely disagreed with it and thought it was garbage. He approved it, and you know why? It was because Planck read Einstein's theory of relativity, and he loved that. He thought, wow, this is great stuff. So somehow, you know, this idea of stretching time and space, I don't know if you have any idea how totally counterintuitive relativity is, but Planck thought, oh yeah, right on with that. But light particles, oh no, that's... But anyway, based on the theory of relativity being also written by Einstein, he thought, this Einstein, he must be a sharp guy. Even though his photoelectric theory is garbage, I'm going to have faith in him. It's just his faith on the person of Einstein. He approved it and figured, okay, I'll approve it, let him publish it, and we'll let, you know, the world of physicists, you know, pass judgment on it. And eventually they passed judgment by giving Einstein the Nobel Prize for that. So Planck flunked out there, but he was a good guy. He gave Einstein a chance. Well, since then, quantum physics has just overturned the world of physics. Things that were total mysteries, completely non-explainable by physics before 1900 became explained. I gave you 2 examples there, and many more things. The stability of atoms. Why are atoms stable? Why don't the electrons just plunge into the nucleus and disappear? Why are they stable? That was a big mystery for a long time. Quantum physics explained that. Why were they? You might have heard of spectral lines. You look at a spectrum of things, the sun or whatever, and you see lines in it. Why do those appear? Quantum physics explained that. Why do things have colors? Why do they have the colors that they have? No one had any explanation. You know, why is an orange orange? Why is an apple red? There was no explanation. Quantum physics was the first way to explain why things have the colors they do. Why do things hold together? Why are there chemical bonds holding things together? Quantum physics explained this. Why are some things strong and some things weak? What determines how strong something is? Quantum physics explained it. Why do things change from a solid to a liquid or a gas? What depends what state it is? Quantum physics explains that. How is magnetism possible? Quantum physics explains it. And finally, the last example, the extraordinary reliability of genetic inheritance. This has to do with the theory of evolution and all. Again, quantum physics explains it, so I'm told. My son has a PhD in genomics and molecular biology. I asked him to explain this to me. He explained it, but I can't remember it. So you'll have to just take his word for it. Okay, so Einstein showed light is made of particles. Everything's solved. Everybody's happy. Now we understand light is made of particles. No. That does not solve the problem, because long before Einstein, it had already been proven that light is a wave, something which is totally different from particles. What is a wave? It's just what you think it is. It's like a wave in the ocean, okay? Moving along. It's something that's going up and down and moving forward as it goes. So that could be a water wave, it could be a sound wave, you know, the sound kind of goes back and forth and it moves forward. It could be a wave of people that's sitting in a stadium and they're moving their cards up and down, and you see the wave moves along. Again, that's a wave. And that had been proven, that light is a wave. How can light be a wave? What is it that's waving? With a water wave, we see it's water. With a sound wave, we see it's air. What is waving in light? Well, it turns out light is electricity and magnetism are waving, okay? A little bit of electromagnetic theory here is the electricity or the electric field is waving up and down in one direction, and the magnetic field is waving side to side in a perpendicular direction, and this sustains itself and it propagates forward. It moves forward for the same reasons that a water wave moves forward. Okay? You can't have that wave in the water, you can't just freeze it and it just stays still and sits there. It moves. It moves. And light is the same thing. And this is why light moves, because it's a wave. So we've got a problem here, and I want to tell you some things about light waves. But first, you need to understand some properties of waves. One property is wave diffraction, and this is like you have a wave when it goes through a narrow slit, a narrow opening, like in a wall. It spreads out. Okay. Here's an example. You see ocean waves. They're coming in from the upper right corner, and they hit a barrier, a rock barrier, and the rock barrier's got an opening in it, and some of the wave goes through that opening, and then it spreads out. And it spreads out, you can actually see the ripples in the sand it makes. It spreads out in this semicircular pattern. Okay, so this is a property of waves. It's kind of like if you drop a pebble into a pond, this picture on the right, it makes waves that propagate outwards. Only with going through a slit, it gives you like half of that. Okay, so that's one thing that waves do. Another thing that waves do is to interfere with each other. Okay, let's say you have two waves. On the left, I showed two waves, and let's say that these waves they're in sync, or they're in phase with each other. They're lined up with each other. You can see that the two waves, they both have their peaks in the same place, the valleys in the same place. They line up with each other. Okay, then you get what's called constructive interference. And those add together, and they make a wave that's twice as big. Okay? Makes sense? Well, they don't have to line up that way. They might be totally out of phase, out of sync. And in this example, where one is a peak, the other one is a valley, and vice versa. When you add these two waves together, it's called destructive interference. They cancel each other out, and they end up giving you zero. Okay? You might wonder about, conservation of energy or something. Don't worry about that. That's all taken care of. But whether the interference is constructive or destructive depends on whether it's in phase or out of phase, or it could be anywhere in between. And here's an exercise you could think about as other examples where things can add constructively or destructively. Okay, so now let's go to an experiment. How did they know that light is a wave? How was it proven? There are many ways to prove light is a wave. This was the most clear proof, the most definitive proof. It was done long before. This was back about 1800, I think, like a century before quantum physics. Thomas Young, he did the double slit experiment. Now, first, let's consider the experiment with water waves. What we're seeing here is actually a photograph of looking down on a water tank. So you've got a transparent water tank with water in it, and it's lit in such a way that you can see the waves. You can see the shadows of the waves, kind of, by looking down on that. So the water waves are coming in from the left, and then we have a barrier there. We have just a wall, and the wall has got two slits. That's why it's called a double slit experiment. And most of the water wave is blocked by the walls, but some of it goes through one slit, and some of it goes through the other slit. And the part that goes through the slit, it spreads out into semicircles. Okay, just like in the other picture I showed you, the water waves. This is what waves do. They go through a small slit and they spread out. So that spreads out into one set of semicircles. The water going through the other slit, the lower slit, spreads out into a different set of semicircles. So you have these two sets, and then these two sets of semicircles, they interfere with each other. Because at some places, they give waves that are adding constructively. You have a peak, on top of a peak, making a double high peak. And in another place, they add destructively. You have a peak length the same as the valley, they cancel each out and they give you nothing. And so that gives you these patterns here, these strange interference patterns. And then if you look over, say on a wall over here, and you look at the patterns, you find that, you know, if you do all the math for this, calculate the angles, you find that at some angles, you get destructive interference and it cancels out and there's no wave there. And in other places, it adds up constructively and you get a double high wave there. And then, you know, smooth transitions in between. So you get this pattern and it fits exactly the wave equations. And you say, okay, this is a wave. We know this is a wave. Well, it turns out you can do the exact same experiment with light. So let's say you create light waves coming in from the side, and you send them they hit a wall, and the wall's got two slits in it. And according to wave theory, each of those slits is going to give you a set of semicircles, and then the two sets interfere with each other constructively and destructively, and you measure the light on a wall over here, and you see you get alternating light and dark regions, and you calculate at what angle those light and dark regions occur, and you find out that it exactly matches the wave theory. Okay, and you can do this, you can change the distance between the slits, the wavelength and the light, everything matches perfectly. So there is no doubt light is a wave. Okay, and this has been known since about 1800. So we know light is a wave, and okay, and let me show you a little bit of animation showing you the wave picture of light. Whoops, have to hit it in just the right spot here. Okay, so we have here light coming out from some light source, and it's creating waves, and then it hits this wall, and some of the light goes through each of the slits, and then you get these interference patterns, and they hit the wall way on the upper right there, and they make these patterns of light and dark, and the theory explains all this perfectly. So that's just the wave view. By the way, this guy, Thomas Young, came up with this demonstration. Very remarkable guy. By the time he was age 6, he had already read the Bible, the entire Bible twice. He had learned Latin. By the time he was a teenager, he was fluent in 13 languages, some of which I'd never heard of before. And then he came up with the RGB theory of the eye, of how we see colors using, red, blue, and green and blue cones in our eyes. He was the first person ever to translate Egyptian hieroglyphics, and he came up with one of the most important experiments in the history of physics, the double slit experiment. So all of this by one guy, Yeah, whenever I want to feel inferior as a physicist, I think about Thomas Young. Okay, so let's look at this. How am I doing on time? Maybe we should take a break.
Yes.
Oh, it's late. We should take a break. Okay, sorry, I get carried away. For me, it seems like we should take a little intermission. So why don't we try to keep it to like 10 minutes? People can, get up and stretch your legs and whatever. You can talk to me or something. And we'll continue.
As long as
I'm gonna try to get in the cover next week. Same time, same station, no, a little later.
Literally, I've got 2 slides. Thanks, Jerry.
Oh, thank you, yeah. I'll read it.
I just found that I had this horrible page with several. Oh, this is Susan.
You did the photon joke. The photon joke, right? Thank you for your and you are Ginger. Ginger. That's another thing, yeah.
This is a factor. Yeah.
Patrick, how do you know?
The top. Oh, yeah.
And then he
He's got a column.
No, I was going to say, yes, I clients for version of
Are you really? That's so great.
Yeah, this is the top version.
Oh, I see.
So Dr. Box, yeah,
So Atash, we were just finding out that Bradley got a blood clot in his leg.
Just found out yesterday. Even like, okay.
I don't know if you read the message, but
No, I didn't.
I better not say break a leg. The Adam down on the
Oh, Adam.
You got baby nucleus and he actually both.
And they're gonna have photons for dinner because they just want to like.
Yes,
Of course. Yes. But he couldn't prove it.
But Ben was that.
People rarely mention that.
When did Jim just have my dad nicknamed him so you're taking aspirin and other meds, right?
I'm taking much stronger.
Yeah.
I've got that.
Still got it.
It's still hurting. I think it's pretty good.
You were just awful. He came to see my show the other night. He was so afraid I could get
I thought you was word out tonight.
light on it.
Well, I could disagree.
Does this mean you gotta change your diet? No, this means that you don't want to see a stroke.
What I want to do, I want to.
You don't want to have a stroke. That's a blood clot in the brain. And see, I had to put Brad on the diet. I put Brad on the really good diet.
Maybe for or and London.com.
you know, what would you want to do for here? But yeah, honey,
I wanna live.
I wanna live. So yeah, Bradley, so, you know, there's treats you can have.
Could we work on this together, because I'm a health freak, and like, I have nothing wrong with me, it's always the food. Here we are, what we eat.
I know he will eat a hunk of vegetables.
Oh, I do. I eat lots of good stuff, and
You know,
then I treat
go
myself.
to a restaurant, you get a salad. You get a nice salad, and you have some.
No, if I'm going out to eat, I can have a salad at home.
You know, a big salad, a big ass salad.
Well, salads are much stuff. I just grab a stick of celery and I just grab leaves of spinach and grab broccoli. I just eat it. It's like taking vitamins. Just eat stuff. You know what I mean?
Because I have a beautiful
It is essential though. I wouldn't be who I am if I hadn't changed my evil diet.
I've been meaning to talk to you about it. You've got to change your ways.
I actually have to go meet the kids somewhere.
Oh,
So
I have to
well, you've heard what I call part A.
Okay, good. And people are just coming in and it's just got life. Take it in there.
It's so funny, because at a certain point,
I like to watch them though. I do like making quantum leaps.
oh yeah. It's very
They
irritating.
actually publish it on art. I wrote it everything.
People really do think it means the opposite of what it is.
It sounds good.
Well, if people don't know what a word means, they assume it means big or important or great.
Yeah, I'm so glad that Ginger is my girlfriend, and I love that. All right, Bradley, I should have to leave, but thank you for.
We're gonna be in cahoots.
Okay, yeah, I'll talk to you about what I sort of eased off on the super diet for Brad, and recently he had a leg problem.
I'm talking about bread and cake.
And it could be something bad, because, I bought some bacon, I actually was stretching it out over 2 weeks of like giving them one slice, because it's so, but I gotta go back, get things unclogged, and then you can do something fun from later, But when I say fun, Bradley, it's easy.
It's easier than quantum. It's easier to It's easier to understand.
You know what, the diet.
Well, I guess at 4:30.
because they continue to lay their money. They don't do bail.
So what is this guy talking
It's you, Haku. Oh, there they are, thank you.
Text me whatever did you send everybody else. And then what do you do? How do you get his information? Oh, that's
I remember he's produced that video. I'm the, you know, it's great.
I know.
Heard that too, you know,
I think that's good.
it just sounds like nonsense when you talk about it.
It's very hard.
It does sound like it. Well, you took more than that. When you get to high
Quite a while back. I used to watch something that he was on television on a regular basis.
Someone sold
I found out biology is the science that smells bad. Like studying different right around as they come back. Physics is the one that doesn't work.
Is physics a short version of physical sciences? I mean, what does the word physics mean?
It has to do with motion and forces and constants.
Yeah, I never had any science classes. The highest math class I had was algebra.
I think I actually know the answer to this.
First time Dad was the existence of Adam, I said, okay, people can talk about it. Ancient Greek was talking about anybody say, hey, they're Adam. He proved that they're Adam. Nobody could
All kinds of
Right. So the answer probably no.
no one can figure out how to
rocks Physics like like two cars crash into each other, one's going forward, one's going back. What happens? Wings hit each other.
It causes more destruction. Yeah, that's for sure. Yeah, that's when they're not in sync with each other. You know what I mean? If they're in sync with each other, then there's not gonna be any action. It's like a friction. And then you got Aleister Crowley, who was into physics too. He was a physics professor. Yeah, he dealt with the space and how it relates to like astronaut, physical beings. Aleister Crowley. Yeah, he was very brilliant. They said that he was into demonology. He wasn't. Crowley? You've heard of Aleister Crowley, right? No, but I heard Neil Gaiman. Oh, he was brilliant. Good Omens. No, haven't. Good Omens. The character. The devil is proud. We've got Anton LaVey. He's like a really good guy, so I'm thinking, I don't even believe in this. No, but I think that it's a matter of opinion, you know? Well, but this is not a Judeo-Christian. Some people believe that it's an actual, don't know I think it's more of a force. Anyway, no, he just reinvented the whole concept. It's a force of negative energy, which is a very childish behavior. That's my opinion.
Is anybody out in the lobby? I don't know. I guess somebody's gonna announce it. We need someone to announce that the intermission is
And he was banging when I went to take that now, it just pissed me off. My whole life, they're telling me you can't divide by zero. And now this is how you basically divide by zero. I only did it. I passed the class. He's like, well, I dribbled. I didn't pass it well, but I was a business major, science major.
So there's nobody in the lobby.
There was one lady, and I told you.
Okay, yeah, I didn't mean for the, we don't have much time left. I was hoping someone would end the intermission, but I guess I'll just say the intermission is officially ended. I have, oh, God, this takes way too long. You know, the problem is I keep getting more ideas to put in this lecture. I guess maybe I need more parts to it. Okay, well, let's move on. Oh, and I guess for people who were late, may not have realized that this is a very momentous occasion. This is, out of all the hundreds of lectures I've given, this is the first one I've ever given sitting down. I got a horrible pain in my knee, which I just found out was a blood clot. So I got here on a walker. This is not usual for me, and hopefully I'll be walking again soon. Okay, so before we talk about the double slit experiment and about is light a particle or is it a wave, let's talk about how we do experiments where we measure photons, because we certainly want to do that to understand this. So you realize that usually when we look at light, we're seeing millions or billions or zillions of photons. Okay, that's why we don't notice the quantum effects. So in order to make the quantum effects clear, let's suppose we have a light source which is very, very dim, and we're getting one photon at a time. So this, so we send one photon out, it goes, then we send another photon out, another one, and so we don't have to worry about them interacting with each other. So there's no question of one photon interacting with another one because our light is so dim. And but we need to be able to detect each one. Our eyes are not sensitive enough to see a single photon. If you sit in complete, total pitch black for half an hour, your eye will get sensitive, most sensitive it can. And then, and I've done this when I'm doing experiments sometimes, you will, once in a while, you'll see a little flashes of light. And what that is that occasionally you just happen to get randomly, like maybe 10 photons hitting your eye at the same time. And that's enough to see. It takes about 10 photons to be able to see it when your eye is in its most sensitive state. So that will happen occasionally in a very dark room. But let's suppose we have a camera. Let's say it's a digital camera. Okay, use modern technology. Of course, none of this was available, back in Einstein's time. But let's just imagine now how we would do this experiment with an extremely sensitive digital camera, so sensitive that one pixel can record a single photon hitting it. Okay. And we're going to take this camera. Okay, we're going to do this experiment in complete darkness, except for this light source is going to produce photons one at a time. And then we're going to record them on the camera. We're just going to open the camera shutter. So when a pixel hits, when a photon hits one pixel, that one lights up and it just stays lit. Okay? And then when another photon hits another pixel, it just stays lit. So when this happens, we'll see, after some time, we'll see one pixel gets lit up, indicate one photon hit it. And then at some time later, we get a second photon, hits someplace on the camera, and a third, and a fourth. And one thing we notice here, each photon is localized. It only lights up one pixel, a single pixel, because a particle of light, a quantum of light, is localized. It can only be detected at one place at one time. A single photon cannot light up two pixels at once, only one photon. The other thing we notice is that the timing is random. Okay, we can't tell the source put out one photon every 10 seconds. We can only tell it this is on average how many photons it's going to put out. You know, cut it down until it puts out. The photons come out at random times that we have no control over and no way to predict. Completely unpredictable and random. We can cut it down so that we're getting on average 1 pixel a second or whatever, but we cannot make them come out at known times. We also cannot make the location. We cannot determine the location. We can set things up so they're more likely to hit here or more likely to hit there, but we cannot tell the camera, we cannot tell the photon where it's going to be or predict where it's going to be. So when we observe these single photons, they come at random times and they come at random positions, okay? So with that knowledge, then let's think about how we're going to do the quantum light experiment with photons. Now the first question we're going to try to answer is which slit did the photon go, or really, did the photon go through one of the two slits? Or did the photon go through both slits? Okay, and the way we're going to tell that is we're going to take our double slit wall, our barrier with two slits in it, and we're going to put one detector right directly behind one slit and another detector behind the other one, and put barriers so that if detector A detects a photon, that means the photon had to go through slit A. And the same thing with slit B and detector B. Okay? So now let's run this experiment where we have photons going through, and we're wondering, does a photon ever go through both slits? And the answer is no. Never, never, never. You can do this experiment, and it has been done billions, zillions, whatever number of times, and what you find is that the photon always is detected at detector A or detector B, never by both. And that makes sense because it's a quantum. The photon cannot be split. It's one photon, so it can only be in one place. The only way that it could go through both slits would be if it's split into two photons. But one photon we define as one quantum. There's no amount of light that is less than one photon, except for no photon. So if you have one photon, it can only be in one place at a time. So we conclude from this experiment that the photon went through one slit or the other slit, or it went through no slits, okay? Now most of the photons just hit the wall. We don't care about those. We don't measure them. But of the photons that are detected, they're detected at A or B and never at both at the same time. Okay? So we go in knowing that a photon never goes through both slits. I hear a lot of physicists say, oh, the photon went through both slits. No, it doesn't. It doesn't. They're doing tricks with the language or something. But you might wonder, well, even if it's a quantum, can it go through both slits? Well, consider, that your hotel room might be both to the right and to the left, or how maybe a car can park on both sides of the street. I mean, why else would they have to have a sign telling you do not park on both sides of the street unless it were possible to park on both sides of the street? And even a dumpster can be both full and empty. It can be empty when it's full. So, you know, who knows? Okay, so let's go to the next quantum double slit light experiment with single photons, okay? One photon at a time. And now, instead of putting detectors right immediately behind each of the slits, we're going to back up the camera. So we're going to go back to a digital camera with many pixels so we can see what's happening. And we're going to move it back. The reason for moving it back is, remember I talked about the diffraction? The light wave diffracts after it goes through the slit, and then the patterns, they interfere with each other. They need room for that. Okay, that can't happen in a very small space. You need a lot of space for this diffraction and this wave interference to happen. So you need to leave a lot of space in here for the diffraction and for them to overlap each other and interfere. So we're going to leave space now. And now we're going to do the experiment again, where we're going to have photons coming out at a single time, one at a time, and detect pixels. So we detect one photon hits the camera over here. Okay, and then another photon. And again, this photon appears, this pixel lights up at a random, unpredictable time, and it hits a random, unpredictable pixel. And we know that every photon went through one slit or the other. We just proved that in the previous experiment. No photon ever went through both slits. So let's keep doing this. And we get a pixel turns up here at a random time and a random time here. And do this over and over and over. And just run this experiment for days if we have to, in total darkness, except for this dim light source, until we get zillions of photons coming through. And what we get is a pattern that looks like this. Now, if we get these light and dark bands, and if you calculate the positions of those, it matches exactly with the wave equation. Okay, exactly. You can change things. This experiment's been done a billion times. It always works out. I did it in freshman physics class. It always works out. Now, how did this happen? We saw single photons coming through, and every one of those photons went through only one slit or the other slit. And we end up with a pattern, which the only way that you can get this pattern is you have a wave that goes through both slits, so you get two diffraction patterns, and the two diffraction patterns interfere with each other to create this wave pattern. How did we get this interference diffraction pattern out of photons that never went through both slits? There was only one coming through the slit at a time. And how did this happen? This is one of the greatest mysteries in all of physics. How did it happen? And now we'll show another cartoon, which shows here. Now we have our something, wave, particle, photons, we don't know what it is, goes into two slits, it diffracts, it interferes, but we end up with one spot. There's just one little pixel, a red spot that lights up. And then we do it again, and again we get one spot at another place. But let's do this over and over and over, and more photons and more pixels lighting up. Let's speed up the motion so we get more and they build up. And after we get enough, this pattern emerges. So this is what happens, even when you're doing single photons. So we said light is a wave and light is a particle. Okay, but a wave is spread out, and the only reason it gives you this pattern is because the wave is spread out and goes through both slits, diffracts, interferes, gives you this pattern. But light is also a particle, and we know that with a particle that it goes through one slit or the other slit, never both slits. You detect it behind one slit or the other slit. So we call this duality, the duality, wave-particle duality, or complementarity, because these two, wave action and particle action, they complement each other. It seems like light, in some senses, it acts like a wave, sometimes it acts like a particle. So what is it really? Okay, we can call things waves, and we can call things particles, but what are they really is something that maybe we can't imagine, we don't have a name for. Maybe we don't know how to describe what is this thing which has both wave particles and wave properties and particle properties, even though wave particles and particle properties are totally incompatible with each other. They're mutually exclusive. There are some examples of this duality, like in art. You've probably seen some funny pictures like this. This upper left, is that? Are we seeing on the left? Is that the beak of a bird, or is that a rabbit's ears? And I like this one below it. You look at it one way, it's a goat that's turned its head looking towards you, and in another way, it looks the goat's ear is the bird's beak. You've probably seen this picture. Look at it one way, you see a young woman looking away from you, or it could be an old woman looking down, forward, and then you see a vase, or you see two faces looking at each other.
Wow.
Here's another example. We have an image here, a very familiar person, and in order to see the other image, we're going to use an optical effect. All we're going to do is stand further away from it. So imagine you're looking at this figure and you get further and further and further away from it. And so as you get further away, it looks smaller and smaller and smaller. To simulate that, I'm going to take this picture and I just, in PowerPoint, I just, drag the corner and make it smaller. So I'm going to take the exact same picture. I swear I'm not making any changes to the picture. All I did was make it smaller, and then it looks like that. So somehow, just like the wave and the particle combined in light, we have two different people combined into the exact same picture, depending on how you look at it. And so it all comes down to the question, who's your best friend, quantum physics or diamonds? Well, this idea of duality and complementarity has also been extended to other fields, like, for example, political philosophy. This idea that two things that are mutually exclusive, they can't exist together, it's one or the other, and yet in quantum physics, they're united into a single thing, into light. This was done, in fact, by a very famous physicist, Max Born. He suggested it could apply to the complementarity of capitalism and communism. He considered those as mutually exclusive, but then he wrote about how you get this psychological motives, synthesis. I don't know, sounds like a lot of BS to me, but the point is that quantum physics is introducing philosophical concepts that can now be applied to other subjects, again, showing how science affects philosophy. Now, as I mentioned, Max Born, very famous, but you may not have heard of him, but he really is famous. How famous is he? He's so famous that he had a Google Doodle in his honor a few years ago. He got a Google Doodle, and this shows him in his office. But this picture of him in his office is missing something, because when he was alive, if you had gone into his office, you would have noticed something. Every visitor to his office, the first time they went into his office, one thing they couldn't miss, it's not shown here, they couldn't miss on the wall, he had an enormous portrait of, Olivia Newton-John? What? Wanting to get physical with physics? What? Why? I mean, he must have been a really big fan, right? And if you'd ask him, he said, yes, is definitely a very big fan of his granddaughter. So I have another interactive exercise. You might think again about applying the idea of quantum duality, quantum complementarity into other fields. So, is there something going on here? Whatever it is, can stop. Okay. So next the question is, okay, so since like sometimes light's a wave, sometimes it's a particle. When? What determines when it is which? When is it a wave? When is it a particle? light seems to follow two different laws of physics. And what determines which laws it follows, it depends on how we measure, what experiment we do. We do one experiment, we show light's a wave. We do a different experiment, we show light's a particle. Yes?
So basically, like anything else you're measuring, or you're looking for, like poisons, you only look for these, you're only gonna find those, you're not gonna find those over.
Right, what you're looking for, you find, which that sounds like it's not objective. That's not the way that science is supposed to be done. Science is supposed to be completely objective, and you're supposed to find things unbiased. You have to have an unbiased mind, set your experiments up so there's no bias. And yet, the experiments I've described, there's no bias involved except for what experiment you choose to do. And so it seems that the scientist is deciding, he's determining the results of the experiment. He's determining what behavior light has, whether it's wave or particle, by what experiment he chooses to do. So it sounds like what light does when depends on us. We get to choose. We're somehow involved in this. Scientists are supposed to be just observers, but it's, people are questioning, well, is it possible to be objective? Is it possible to be an impartial observer? Is just the fact that we're the ones looking at things, measuring things, observing things, does that make us part of it? And now we can't just observe it independently, we're influencing it? Raises some strange philosophical questions. Okay, the next thing I want to describe, I need to talk about a beam splitter. And that's a beam splitter, not a bean splitter or a bee splitter. For those of you who are familiar with the Santa Rosa Anderson, Happy, and I forget their names. Okay, so a beam splitter is a partially reflecting mirror. Okay, so it sends light in two different directions. You put light into it, and it sends it two ways. So, and let's just suppose it's 50-50 to keep things simple. So on the left, and it's always designated as BS. So if anyone asks about beam splitters, it's just a lot of BS. So on the left, we have the wave picture of what it does. So we have a strong wave coming in, and then there are two waves. Half of the power in the wave. You get a wave with half of the power going through, and a wave with half of the power getting reflected. But now from the quantum view, let's say if you have one photon going in, the photon cannot be split. It's one quantum. So the photon either goes through or it's reflected, not half and half. So that's saying, on average, if you send in two photons, on average, half of them are going to go one way, and half of them are going to go the other way. So if you put in two, they can both go one way, or both go the other way, or one each. But on average, you put in a million photons, 500,000 go one way, 500,000 the other way. Okay? So now, knowing what a beam splitter is, now let's look at a variation on the two-slit experiment. Okay, so again, we have our light source on the left, which is putting out, let's say, single photon, one at a time. And instead of two slits, we're going to have two mirrors. Okay, so some of the photons go out in all directions, and some of them hit the mirror up on the top, some of them hit the mirror on the bottom. And we set up the geometry so that the two paths cross. And there are two detectors to see which way they went. Well, imagine if this beam splitter is not here, then if detector 1 sees the photon, we know the photon reflected off the mirror at the top. If detector 2 sees it, we know it reflected off the mirror on the bottom. But if we put a beam splitter right at this intersection, then we no longer know which way the photon went. It could have reflected off the mirror and then gone through the beam splitter or reflected off the mirror. We don't know anymore. And what we find is that if we put the beam splitter in, we get a wave pattern, and if we take the beam splitter out, we get a photon pattern. Okay? So by putting in the beam splitter or taking out the beam splitter, we can determine, are we going to see a wave behavior or are we going to see a particle behavior? Like I said, we can determine. But now here's where it gets really interesting. Let's suppose, this is called the delayed choice experiment. Let's suppose that the photon, starts, and the wave, whatever, starts going out. It reflects off the mirrors, and the waves or photons or whatever is coming back from whatever path, they're approaching this intersection. Okay, so whether they reflected off both mirrors or just one mirror has already happened in the past. Now, we're going to use our free will, and we're going to decide, do I want to put the beam splitter in or leave it out? If we leave out the beam splitter, we get a particle photon pattern. If we put in the beam splitter, we get a wave pattern. So not only can we determine whether we're going to get a wave or a particle pattern, we can determine it even though it happened in the past. Whether the wave reflected off both mirrors or the particle reflected off one mirror, that already happened because we can calculate how long it takes for the light to go. We know how fast light is. We can wait until after it's already reflected, and then after it, we can now change the pattern for things that already happened. So it sounds like we're changing the past. Well, if we do this on a tabletop, everything happens so fast that it's hard to tell what's in the past or not, okay? Because the time difference is nanoseconds. So, you can hardly even measure whether this happens. But let's think bigger. Let's take the light from the sun and put mirrors and then combine it. And now we've got minutes for this to happen. So we can do an experiment where by choosing to put in the beam splitter or not, we can change what happened minutes ago. Well, let's not stop there. Let's think bigger. Let's take light from the nearest star. And now we can change the past, what happened years ago. Or look at a more typical star. We can change what happened centuries ago. Or let's look at light from another galaxy. We can go back in time, change the past millions of years ago. Or let's not stop there. Let's look at things that are much, much further. We can go back in time and change what happened billions of years ago. Okay? So you're looking at this and thinking, oh, okay, that's fine in theory, experiments. Well, all of these experiments, including the last one, have actually been done. These experiments have all been performed for all these cases, and even in the case changing the past billions of years ago, it worked. It worked. They put the beam splitter in, they get a wave pattern, they take the beam splitter out, they get a photon pattern, even though the reflections that determine which pattern it is happened billions of years ago. Well, the first thing you might be wondering, how could they possibly do this crazy experiment? Well, it was made possible by, yet again, Einstein. Einstein, one of the other things he did later on, come up with the theory of general relativity, theory of gravity, and he figured out that you can use gravity as a lens to focus light. So we have the picture reversed this way. If I turned it over, then you couldn't read the writing. But now we have the light source on the right side. So let's say we're looking at something which is billions of light years from Earth. So this is something that has been around since almost the beginning of time, almost going back to the Big Bang, something that is that old. There are things like that, and we can see them now. And let's suppose that there's some galaxy, not just any galaxy, a massive galaxy. You need a really big galaxy to do this. The galaxy happens to be in the right place so that photons traveling one path are bent around So now they're going towards the Earth. And let's suppose there's a second massive galaxy that can direct photons going in a different direction, also direct them towards the Earth. And now you see how this looks like the experiment with the two mirrors, where the galaxies, each of these galaxies is acting like one mirrors, and they're defining two possible paths that the light waves or photons can direct it. And now we have a telescope on Earth, a very powerful telescope that can see light from this distant quasar, and it can see light that's coming from both of these paths, and now put a beam splitter in that light, and if we put the beam splitter in, we get a wave pattern. If we take it out, we get a photon pattern. So somehow we're changing light that reflected by a wave or photon pattern billions of years ago. Well, okay. Are we really changing the past? Okay. Nobody believes we're actually changing the past billions of years ago. So there must be a less absurd explanation for all this. And the explanation is that light does not go back and forth between being a wave and being a particle. Okay? It may look that way to us, but light doesn't do that. Light just is not understandable in that way. Basically, the answer is, we don't know what light is, okay? You know, if we assume that light is something that can be a wave or a particle, we come to the conclusion that we can change the past billions of years ago. Okay, well, which explanation is more ridiculous? That one, generally people go with the idea that light is indescribable. They'd rather believe that than changing the past idea. By the way, the guy who came up with this experiment, John Archibald Wheeler, he's written like the classic textbook on the quantum theory of gravitation. Some interesting things. He worked with Niels Bohr. We'll talk about more. He was the first. They were the first to split the atom, nuclear fission, the basis for all nuclear reactors currently in the atom bomb and all that. He was a mentor, the advisor to Richard Feynman. Many of you have heard of, I'm sure. And he also came up with the name black hole. He was not the first to find a black hole or to come up with a theory of the black hole, but he did come up with a name. He gave it that name, and it stuck. Okay, another interactive exercise. Oh my gosh. How did I do this? I'm only a quarter of the way through.
Wow.
This is part B of 4, this is the start of part B of 4 parts. How did I do this? This whole talk used to fit into about less than 2 hours. I don't know what happened. Well, let's go on a little further. Yeah, okay, all this gets repeated. And the recap, we can skip all this. Okay. Okay, so what did Einstein think of all this? People were talking about light is changing back and forth between being a wave and a particle. What that's about? What's that all about? That's silly. You know, I mean, of course, they're all brilliant Nobel Prize-winning physicists that were coming up with these ideas. But Einstein thought that's a bunch of hooey. You know, clearly what's happening is that the particles are always there, the photons are always there, and the wave is always there. He called it a ghost field. They're always both there. You always have both. That's the way he saw it. And that idea got developed by Louis de Broglie, we'll talk more about later, came up with a pilot wave interpretation, pilot wave theory, developed further. You may have heard of that. But basically the idea is this, okay? Let's say we have a box. We don't know what's in the box. Sometimes we hear a roar come out of the box. Sometimes we hear a buzzing noise come out of the box. Well, what's in the box? One answer. There's some strange being in this box, and it can transform back and forth between being a lion and being a mosquito, right? You know? Well, And when it transforms, it depends on what we do, what kind of experiment, and what experiment we plan to do in the future determines whether this strange creature decides to become a lion or be a mosquito. Or answer B, we can say, you know what, there's a lion and a mosquito in the box. Done. Okay, this is Einstein's way of looking at it, and other people who came up with the pilot wave theory. And, you know, Occam's razor cuts out the unnecessarily complex answer. Seems to be common sense. There's a lion and a mosquito. Okay, now just apply this. Instead of lions and mosquitoes, let's talk about waves and particles. So it seems to me, this is my own personal opinion, and is definitely not accepted by all physicists for, I don't know why, but like a wave and a particle. You have both of them, okay? And it's called a pilot wave because the wave pilots the photons. The photons are guided by this pilot wave that's guiding it, okay? The photon went through one slit. As the experiment showed, the photon never goes through both slits, but the wave goes through both slits, and then the wave guides the photon. So the reason the photon lands in a place that is affected by the presence of both slits is because the wave knows about the slits and it's guiding the photon. The photon doesn't have to go through both slits because it's guided by a wave that did. Okay? We can only detect photons. The wave is not detectable. Okay? We only know about the wave by seeing what it does to the photons. And I would say it resolves the mystery, and it resolves the wave-particle duality. And this applies for any other kind of quantum. But, and also there's a theory for this. And it's based on the wave equation. Anyway, somehow this theory is very unpopular among physicists. In fact, de Broglie, when he tried to promote this theory, he was so ridiculed for this silly theory that he caved into peer pressure and he just dropped it and said, okay, forget about it. That's how unpopular it was. And it was picked up later. But I think whatever objections they had could be fixed. Yes.
But if there's no way of detecting the wave.
You can't detect the wave. The only way you detect the wave is by seeing the behavior of the photons that are guided or piloted by the wave. That's it. That's the basic idea. And you can actually calculate the patterns that photon travels in the double wave experiment, and the patterns depend on like where in the slit they go through. And you might say, well, so there's a hidden variable for position within the slit. You might say, well, photons, they're not going in straight lines. Well, we already know that diffraction means that light doesn't go in straight lines all the time. Okay? Light spreads out from diffraction, so that's not news. So if it's going to not go in straight lines, then why not go in these lines? Maybe. And this could apply to any particle. Okay, but as I say, my own opinion, hey, that solves the mystery, but you will find the great majority of physicists will still say wave-particle duality, still an unexplained mystery. This doesn't answer it. Go figure. Okay, let's see. We said we were going to end by 4:15, but should I keep going a little further?
Yes.
Okay. They said I could go till 4:30. No way I'm going to get through the first half through part one. Sorry. But next, let's talk about uncertainty. Okay, because I've talked about random, non-predictability of things. There are things that are uncertain. Now let's look at what are some reasons why you might be uncertain of something, like in a scientific experiment. Well, your equipment. Scientific equipment is never perfect. It's got its own limitations, okay? Maybe it hasn't been developed enough, maybe it didn't have enough money for the best equipment. It's got limited precision, so you're uncertain about you know, how much more precise the answers might have been if you had better equipment. Maybe the equipment hasn't been invented yet. Maybe the technology has not advanced far enough for being more certain about something. Maybe we're not smart enough yet. Okay, we just haven't come up with good enough ideas to figure out, to figure things out. It's going to take time. Work on this more, and eventually maybe we'll get smart enough to be able to reduce our uncertainty. And maybe the best idea just hasn't hit us yet. Or maybe that's not the right conditions. Maybe in order to reduce the uncertainty, you have to have just the right conditions. The moon has to be in the right place, the right phase or whatever, or there has to be sunspots or whatever. Maybe we haven't seen the right conditions. Yes, question?
Do you think there might be like a certain spectrum of light that we haven't discovered, like ultraviolet, that might detect the wave in some way?
Oh, we are well aware of the entire spectrum of electromagnetic radiation. It's all well known, except out beyond cosmic rays. When you get to very high frequencies, we haven't seen that yet, just because we don't have the equipment. But from there on down, all the spectrum, gamma rays, X-rays, ultraviolet, infrared, that we've, explored thoroughly. Yeah. Okay. But these are all reasons that we could overcome in the future in principle. But at some point we reach a limit of uncertainty. We can look forward to becoming more and more certain until we hit the Heisenberg uncertainty principle. So Werner Heisenberg in Germany came up with this. He also invented a matrix description for quantum physics. And what he showed and proved, and has been proven, has been that there are fundamental limits to how certain we can be about anything. That it's not limited by how smart we are, technology, the condition, or anything. There's like a limit which is unpassable in theory. It could never, ever be passed. No matter how smart we get, how good our equipment gets, how far technology advances, it can never be passed. There are things that are unknowable, that remain uncertain and will always remain uncertain. It's as if a precise answer doesn't even exist. It's as if reality itself has a fundamental inherent uncertainty in it. That reality is uncertain. That's what it's suggesting. These limits have been proven over and over again. Many, many experiments over for nearly a century have proven that these limits are there. Okay, it's hard to imagine. You can imagine why you can't measure things, but you imagine that the reality of it isn't precise. There's an uncertainty there. Well, what kind of things can we be uncertain about? Well, I mentioned about random. Does the photon go through slit A or slit B? We can't predict that. It's random. Where does it land on the camera? When does it land on the camera? We can't predict these things. They're uncertain. So it might not just be in precision, but in big differences. Does it land at this end of the camera or that end of the camera? Going through this slit or that slit? We're uncertain about things that are unknowable. Not only do we not have a theory which tells us, where and when a photon lands and what slit it goes through, but we have a theory which proves that it is absolutely impossible ever to have such a theory. It's impossible ever to measure that thing. It's unmeasurable. It's a strange concept, to think that maybe reality itself has uncertainty built into it. And there's this inherent randomness. Now, we don't usually see this because, like I said, a quantum is usually very small. And so we don't see one photon of light. We see zillions of photons. And what we see is the average behavior. So we can predict the average behavior using statistics, okay? And in that case, the uncertainty becomes unimportant. It's only when you look at one photon or a handful of photons, where these effects become important. But it turns out these effects become very important. And without these principles, we could not have cell phones, we could not have digital computers, digital cameras. None of these things that I showed would exist without understanding this basic principle. Well, once again, Albert Einstein was looking at what other scientists were doing with the theory. He invented quantum mechanics, he and Max Planck invented it. And what are these other guys doing with his baby, his brainchild? Once again, he's griping about it. What's this idea of randomness? He did not like this uncertainty theory at all. And he came up with this famous quote, God does not throw dice. He wasn't making a religious statement. He thought of God as nature, the universe, or whatever, in a more abstract sense. But he's saying, he can't believe that there's randomness in the universe. That cannot be. Well, Niels Bohr had a great comeback to that. Stop telling God what to do. Just accept it. This is the way it is. It doesn't have to be how you like it. But somehow Albert was never convinced. By the way, we'll be talking a lot about Niels Bohr. He came up with, you've probably heard of the planetary model of the atom, where you've got some things in the center, kind of like the sun, in the nucleus, and then you've got electrons orbiting around it. Niels Bohr came up with that. So we're talking, even though I'll say a lot of things against Niels Bohr and his philosophy, as a physicist, he was brilliant. One of the greatest. Okay, this uncertainty principle, it might sound like it's just a vague notion, we're kind of uncertain, things are kind of, no. It is not. There's an equation, an exact equation, okay? I've summarized it here. It can be expanded and, it can be made more complicated to find these terms. They have very exact equations for exactly how much uncertainty there is. It doesn't apply to your uncertainty because maybe you're not smart enough, your equipment's not good enough. This applies to the fundamental, inherent uncertainty that is inherent in nature itself. And it applies always, okay? So physicists are quite certain as exactly how uncertain they are.
So uncertainty is a thing, almost, in a sense.
Yeah, uncertainty is real. There's something very real about it. And we've got a billion experiments proving that. And we can tell you exactly how uncertain it is. So what's the big deal about this? Well, before quantum physics, it was always taken the laws of physics were deterministic or mechanistic, mechanical. That, given all the knowledge about something, the laws tell you how it happens. Given, if you know everything about the present state of the universe, you could predict its future state. But that says something interesting about philosophy, because how can there be free will if you can predict exactly what's going to happen? If somehow you had complete knowledge of everything in the universe, every atom, every photon, where is it going, what is it doing, what is its energy, if you somehow could have all that knowledge, you could predict, but based on the old theories of physics, you could predict exactly what's going to happen next, and after that, and after that, and you could predict everything that will ever happen. Well, then how can anyone have free will that is unpredictable, if that's the case? So, quantum physics changed that. Quantum physics makes the laws of physics they no longer tell you what happens, they tell you what might happen. They tell you how likely it is that this would happen, how likely it is that that will happen. They're statistical, they're random, they're non-mechanistic. What's called quantum mechanics has been suggested should be called quantum non-mechanics because it destroyed the whole mechanistic idea. And it allows this uncertainty that things are unpredictable, and maybe that's the key to why can free will exist? Free will is a big question of philosophy. Maybe the reason that free will is possible is because of quantum physics. Think about that. You talk about the effect that physics can have on philosophy. There's a big one. Okay, gosh. Oh, I gotta get to the next joke. I gotta get through this. Okay, Erwin Schrödinger. came on the scene, an Austrian physicist who escaped from the Nazis, crossed the Alps into Ireland. He figured out a way to describe quantum physics. He said, well, we have particles, we have quantum particles, but somehow they're connected with waves. Let's take wave equations and a wave function, and it doesn't tell where the particles will land, but it tells us how the wave will determine the probabilities of what the particles will do. And this is kind of addressing the wave-particle duality, where there are waves that don't, because of a quantum uncertainty, they can't tell what the particles will do, but they can tell the probabilities that it will do this or that. And these equations turn out to work extremely well. Basically, these equations are taken as absolute fact. They've been proven over and over again. And incidentally, yes, as he was escaping through the Alps from the Nazis, he did sing "The Hills Are Alive with the Sound of Music." And then Max Born, remember him, Olivia Newton-John's grandpa, he explained what's been called the Born rule. The significance of his equation, it doesn't tell what happens, it tells how likely each possible outcome is. Okay, for example, the wave function, it's always written as this capital psi Greek letter. The wave function of the photon could be, for example, it could be 50% the wave function of a photon that goes through slit A, and 50% the wave function of a photon that goes through slit B. And what this means is that there's a 50-50 probability. Okay, if you set this up symmetrically, that's what the wave equation is telling you. But it can do a lot more. It can actually predict the patterns and all. It can tell you, on average, how these photons will behave. So quantum physics says we cannot predict the future. Okay, we can never predict the future. We can only predict the statistical trends, what will happen when you look at a large number of quanta. Oh, by the way, the Born rule, it's a rule, it's not an identity. It is not the Born identity. Okay, not everyone was happy with this equation. Okay, quantum physics is just getting stranger and stranger. Wolfgang Pauli, the great physicist, physics is very muddled. It's much too hard for me. I wish I were a movie comedian and never heard about physics. Really, one of the greatest physicists of all times. Quantum physics broke him down and made him wish he'd become a comic actor. Werner Heisenberg. The more I think about Schrödinger's theory, the more repulsive I find it. Getting a little emotional here, do you think, for a scientist? Schrödinger himself said it was probably not quite right. In other words, it's crap. And Erwin Schrödinger himself, what did he say about it? I do not like quantum physics, but I'm sorry I never had anything to do with it. So this equation, which, by the way, as I mentioned, was proven to be absolutely true, no doubt, was driving everyone nuts. Okay, I had to get to this. This is so good. Erwin Schrödinger was an interesting character, by the way. Here's a photo of Erwin with seated next to him is his wife, Anne-Marie Schrödinger, and the woman standing behind them is Hilda March, who is the wife of Erwin's assistant, Arthur March. And Hilda also has had the distinction of being the mother of Erwin's son. So there were interesting things going on here. Not all physicists lead boring lives. Now some of you might be feeling sorry for poor Arthur March. Oh, poor Arthur March. His wife is fooling around with his boss. Well, before you feel sorry for Arthur March, one thing to keep in mind is that Arthur March got a really nice position, a really nice job out of this, because when Erwin Schrödinger got to Ireland, they set him up. Oh, the great Schrödinger, yes, you have a lab here at the Institute, and we will hire an assistant for you, any assistant you want, just name it. And everyone said, my assistant must be Arthur March. You must bring him out here from Austria and make sure he brings his wife with him. So Arthur got a real nice position out of this. And also another thing to take into account is Arthur March, he also had another woman on the side besides Hilda. And as you've probably guessed by now, that woman was, yes, Anne-Marie Shorter. So this photo was, okay, I gotta wrap up. I just got one more joke. It's so good. I didn't think it up. This photo was very hard to find. I searched everywhere for a photo of the three of them. I finally found it in a Korean newspaper. Very hard to find. And the title of the Korean newspaper was that. Does anybody here read Korean?
It doesn't look like.
Okay. Oh, is it? Well, maybe it's Japanese or something. I don't know. I ran this through Google Translate, and the title of this article, who said that science-men wouldn't slap their sisters? Compared to Schrodinger, you are weak. No.
What does that even?
I don't know. It's weird. But a friend of mine, I guess some of you probably know Weingarten. Anybody? Okay, Weingarten, he was here, the last time I gave a lecture here, he was here, and he heard this story, and he made it a very interesting observation. He said, now remember the Schrodinger wave function for the double slit experiment, and we wrote it out, we said the wave function, this psi, of the photon can be described by the wave function as 50% of the wave function for slit A, 50% for slit B. And what this is saying is that the photon had a 50% chance of going through slit A and a 50% chance of going through slit B. So then let's ask the question, what is the Schrodinger wave function? What does the Schrodinger equation say about the wave function for Erwin Schrodinger himself? What would his personal wave function of his be? And my friend Weingarten came to the conclusion, well, his wave function, miraculously enough, is almost identical to the wave function of the photon in the double slit experiment, because he too had a 50% chance of going through slit A and a 50%. Oh no. Okay, on that note, we need to end. Right?
I was just standing up.
Oh, you're just standing? Oh, no one's kicking us out?
No.
Should I continue?
I think it's a good inclination.
Maybe more short.
Should I?
Good note to end on.
People think I should, is that a good note to end on? I have so much more material in part one.
Go on.
Next
I
time.
think I should go on? Okay, well,
Yeah.
okay, let's go on. I mean, someone should kick me out, right? Okay. So, on that note, let's go on to, we've been talking about light, but some guy, very interesting looking guy you can see here, a duke, the Duc de Broglie, Louis Victor Pierre Raymond de Broglie, the seventh Duc de Broglie. He came up with an interesting idea when he was, oh, maybe I should quit this one.
Bye, Bradley, sorry. Thank you.
Okay, we'll pick up here next time, and then we'll figure out what we're gonna do about how you feel this material.
I agree.
Sorry.
Hey, can I just ask you a question?
Okay, so,
I second the motion.
yeah, we'll call it quits here, and next time we'll pick up with Louis de Broglie.
I'll be here next.
1 week later, next Saturday, 2 o'clock. Just like this week.
This is just a brief comment on the nature of physics and metaphysics. In some ways, we don't know what either thing really is. And there is some kind, it's sort of the philosophical thing, it's kind of the same thing. You know, that would be a fun thing for you, I think.
Well, metaphysics is like part of philosophy.
Right, that's what I'm saying.
But philosophy and physics are very different things.
Right.
And what's strange is that we have physics that all physicists agree on. There's no doubt, nobody respectable suggests that quantum physics is not absolutely proven, 100% true without any doubt at all. And yet you get to the philosophy and the metaphysics, and they're all disagreeing with each other. They're saying this and that.
And you're supposed to
Great minds
the same.
completely disagree.
It's all supposed to be one thing in some sense, you know.
Yeah, and that just shows you just how confusing quantum physics is. This has upturned the world of physics in an unprecedented way.
I sometimes think that metaphysics is in those cracks, that uncertainty of physics. Somehow those cracks, there's a seam that you're seeing together. You know what I mean? It's just the wildness of
I
that
don't
idea.
know. Any other thoughts on that, or any other thoughts on that idea, or?
No, just that Einstein himself acknowledged the existence of metaphysics. I mean, Einstein himself, you know, I forgot how, but he acknowledged the viability and the existence of this. It's beyond physics.
Well, yeah,
It's beyond physics.
you know, I said Einstein couldn't, didn't like the uncertainty principle. Eventually, Einstein had to admit it's fact, because the experiments prove the uncertainty principle. So
But what's fact?
you may not like something, but stop telling God what to do.
Right.
This is the way it is. Face it.
And then, of course, if he believes like in a
One
Spinoza
thing
God,
through the other.
there's sort of an illusion of nature
Yeah.
and God. That's what I'm saying. That's the kind of thing that's what Einstein said he likes Spinoza's idea.
Yeah. Most physicists like Spinoza.
Damn, so funny. Thank you.
Is there some overlap that maybe was being mentioned here a few minutes ago, that in the sense that, say, when a person dies, do they weigh exactly the same? Or if they weigh a little bit less, can they say that because the soul has departed its body?
Yeah, does the soul have mass? Well, the first question is, does the soul exist? But certainly if the soul had mass, then physicists would say it must exist if it has mass. But I'm almost certain that no one, surely no one has ever proven that a soul has mass.
Of course.
Or energy.
Einstein is
Energy,
dead.
measurable energy.
Oh, right, yeah, measurable. Would it be like a picogram?
There is no
Milligram.
scientific evidence for the existence of the soul.
And I think, because Einstein is dead, there's probably a lot of people who are trying to quote him to fit their own narrative, such as a quote that I heard, whether it's real or not, is something like, since matter cannot be created or destroyed, then I guess somebody interpreted that as that our consciousness doesn't necessarily cease after we die. And what will be your comment on that, Dr. Bob?
Well, the first thing is I can't believe people are saying, since matter can neither be created or destroyed. Have these people never heard of the atomic bomb? Have these people never heard that E equals MC squared? Have these people never heard of nuclear reactors? Are these people living in the Stone Age? Why would, I thought it was pretty well known that matter certainly can be created or destroyed, and I'll talk about some examples of that come from quantum physics.
And then just briefly, so to exist, that's the whole thing where metaphysics and physics. Physics is all about stuff that exists. And so is metaphysics.
Yeah.
So that's where there's this intersection.
Well, the difference
what
is that
existence?
Physics is, it's supposed to be about things that are unprovable.
Yeah.
That are provable. Provable and are proved. Which makes me wonder if string theory is physics. People get all excited about string theory, and I say, there's no scientific evidence for anything in string theory.
Yeah. Right.
It's an excursion into something that they're hoping one day there will be evidence for.
Yeah.
Until then, I don't know, it's not physics.
It's looking weaker all the time from what I hear.
Yeah.
They're just stringing them along.
Yeah, exactly.
Boom.
Yeah, I don't understand why people get excited about string theory. I don't know, string theory is more like, physics masturbation or something.
I thought about that too.
They're not proving anything.
I resisted.
But the idea is that someday it will be proven, or something to be proven. But I don't know. I don't care for
That's my mom
string
quote
theory.
it's, said to his students, teach thy tongue to say, I do not know, and thou shalt progress. Like,
Right, so you have to accept what you don't know.
I don't know.
You have to accept what you're uncertain about. And it's been proven that there is uncertainty, always uncertainty. There are things that are unknowable.
Uncertainty is actually a thing. That's where's my mind.
Yeah.
There's an equation for uncertainty.
Yes.
Yeah, I just wanted to ask, there was that history about Einstein and Bohr having these debates over foundations.
Oh, I'll talk much more about that.
Well, I
I'll
just
talk a lot
wanted
about
to know your opinion on it. What do you think, how do you think they would have reacted if they had seen Bell's theorem and the experiments?
Oh, I've been wondering about that. I'll get into that later, about Bell's theorem and
I mean,
there are much bigger mysteries.
Well,
to
what do you
solve.
think their reactions would have been? Because
We all wish we knew. I wish that Einstein had lived long enough to see the demonstrations of Bell's theorem, because if he had, surely he would have found the holes in them. He would have found the holes there. I'll talk about this in part 2. Now, there are other people who claim they have found the holes, but they're not famous enough that anybody listens to them.
But there have been a lot of experiments with the close.
There are a lot of experiments, and last year, 3 of the people who did experiments got the Nobel Prize for it.
Yes.
People who did the experiments on applying Bell's theorem to quantum entanglement. They got the Nobel Prize for it, but somehow I just feel it deep inside that there's an explanation for why they were wrong, and if Einstein were still alive, he would have found the explanation and people would have listened to him. But I don't know the explanation. So that is the biggest mystery. The particle wave complementarity, I think that one's solved. Pilot wave theory, solved. But very
Do you want to
few
explain what
others.
you were just talking about now with Bell's? You're going to explain, tell us what.
Well, I'm gonna be spending, I've got many slides about that.
Okay, good.
And it comes near the end.
Okay.
That's in part D.
That'll give me that good.
That's in part D. We get to Bell's theorem.
Okay.
Yeah. So part B, we'll talk we kind of got into part B. We'll be talking about the strange things that come from quantum uncertainty and antimatter. And then part C, we'll be talking mostly about the cat, Schrödinger's cat, and interpretations. Then part D, we'll get to quantum entanglement and the really the biggest mysteries that I think that the biggest mysteries in the history of science.
And does that start at 2 p.m. also?
Yeah, let's start. It's supposed to start with the beginning of part 2 or part C. This is
You got to consider writing.
the idea was that it was going to be 4 one-hour lectures more or less, but it's not fitting.
Articles published.
It's not fitting.
But a book is a good.
Are these slides online, are they available to view?
No, I don't like to release them.
Yeah, I thought I saw something that they were
They're putting. I think they put it on YouTube. There have been a number of people who have taped some of these lectures, and they put those up. And